Okay, welcome back. We have reached section 4.3, the Ito integral for general integrals, for general processes. Whereas in the previous part in section 4.1 and 4.2, we have focused on simple processes and defined the Ito integral for simple processes. Here we will go towards general adapted processes. Before we will start with the general adapted processes, however, we will go quickly over what we have seen in the previous video. We will write down what we have done. And in this video, I will just give you an outline of how to do it in general, because we would need a good basis in measure theory to do it rigorously. And we're not assuming this background in this course. So here it will just be an outline, and those of you interested can look in books for the details. Okay, remember that we start with the Brownian motion, Wt, t greater or equal to 0. And a filtration script f of t, t greater or equal to 0 for the Brownian motion. And when we write for the Brownian motion, this means that this is not just a filtration, but it also means that Wt is Ft measurable. It means that the process Wt is Ft adapted, and if S is less than T, then Wt minus Ws is independent of Fs. So we are in a world where there's a lot of information known already. Yeah. Now let's continue. And so what did we see in the previous lecture? We have seen that we defined a delta t, t greater or equal to 0. And that was an adapted simple process, adapted to the filtration with a partition, underlying partition of 0t, because we go to a simple process and then we need a partition. We had our time frame 0 to t because we look at financial contracts in the future that run up to time capital T. And this partition that was as follows, from 0 to t, we said t0 is 0, is less than t1, less than t2, etc., up to tn, and tn equal to t. Now these adapted simple processes, they were defined as follows. Delta t was the sum, I runs from 0 to n minus 1, delta ti times the indicator function of the interval ti to ti plus 1. And if we look at this carefully, we see that it is in fact the value of delta at the left side of the interval, at ti, that is the constant which is in front here. And the indicator function, of course, is 1 when we are within this interval between ti and ti plus 1. And it is 0 elsewhere. And of course, this is a random variable. So therefore, we have the omega here and we have the omega here. This is a random variable. This process is a random variable. For such a process, we have defined the Ito integral. And the Ito integral, we denoted it by IT. And it was defined as the integral from 0 to t of this delta u dwu. And u is the running index. Integral from 0 to small t of delta u dwu. Now, we have defined that as follows. That was the sum for simple processes, right? The sum I runs from 0 to k minus 1. Delta ti, again, the left side of the interval, times this Wiener increment w, the Brownian increment wti plus 1 minus wti. These are all the parts up until wtk, up until tk, plus the last part, delta tk times WT minus WTK. And recall that we had our interval from 0 to T. And it was partitioned into n intervals like this, etc. Then here we have our Tk. And in this interval between Tk and Tk plus 1, we had our T. And our integral runs from 0 to T. So it runs up all the way up until here. The first parts are these parts and that very last interval that is written down here. Yes. And now if we look at properties, the properties, well, first of all, recall that we said we have continuous paths, because notice really the variable t is only in this part. Yeah. It's only in this last term. The first part here, these are just constants. Yeah, they are all constant. And the part that depends on t is actually only here. Yeah, so we have here a linear combination of constants plus a linear combination of a function which is continuous. So it is continuous in total. Let's look at the other properties. Well, we have seen that I0 is equal to 0, because an integral from 0 to 0 is equal to 0. We have seen that this is in fact a martingale, right? So IT, t greater or equal to 0 is a martingale for these simple processes. The expected value of IT is also equal to 0 because of the martingale property. That was easy to show. And finally, an important one was the variance of IT, because the expected value is equal to 0. The variance is equal to the second moment, so the expected value of I squared. And we can write that out in integral form. That looks like this. The expected value of the integral from 0 to t delta u dwu squared. And then we had this handy formula, convenient handy formula that essentially brought us this square inside the integral. So in fact, with the help of the so-called Ito isometry, we know that this expectation is equal to the expectation from 0 to t of delta square u du. Yeah, recall that dw was equal to dt. And in this case equal to du. So here we essentially take the square inside, and what remains is a classical, a well-known integral, a very convenient integral. So the variance is given by Ito isometry, and this is a very convenient formula. So let's now look at an outline on how to extend the definition to general adapted processes. So we will extend the definition to the general adapted processes. It's just an outline. Again, you have to put some conditions in order to make it work. And well, we mentioned adaptive processes here. We talk about adaptive processes. Adapted to the filtration of the Brownian motion, that is. So the Brownian motion is given, fixed, with its own filtration, and given these objects, you are defining the Ito integral. Again, for things to work properly, you have to put an extra condition, which is here, in fact. So this is mainly a technical condition. We have to take limits, and we have to be sure that these things converge. So we restrict ourselves to the integral 0t. As you see here, we restrict ourselves to the interval 0t, and we have to demand that this integral, the expected value of the integral from 0 to t, delta square t dt, that expectation exists. And basically, that tells us that we assume that the variance is finite. So this reminds you of the Ito isometry, And so in a sense, this is telling you that the process must have finite variance. Yeah, and it's used to resolve some convergence issues. It's needed to approximate any process in L2 by simple processes. So let delta t greater or equal to 0 be an adapted process. So again, delta t is then ft measurable. It satisfies our technical conditions in order to resolve some convergence issues. Then we can approximate delta in L2 by simple processes. And that goes as follows. We choose a sequence of increasing partitions, and we recall that these partitions we have earlier denoted by calligraph P, Pn. And Pn is in fact a partition of the time interval from 0 to t in this case into pieces. So we partition it into mn pieces, the number of points in the partition n, so related to n, the number of points related to n in this partition. And t0 is equal to 0, it's less than t1, etc., up until tmn, which is then equal to capital T. And we have these increasing partitions in such a way that we increase the number of points in the interval. And if we increase the number of points, then the size of each interval gets smaller and smaller. And in the limit n to infinity, the size of the maximum interval in Pn goes to 0. Yes? So for each Pn, we associate a simple process, and this simple process is delta sub n related to this partition, and t runs from 0 to capital T. And this simple process is defined as follows. Delta nt is the sum I runs from 0 to the number of points in that partition, mn minus 1, times delta at point ti, again, delta in the left side point, times the indicator function, which is 1 in the interval ti to ti plus 1 and is 0 elsewhere. So we have our timeline from 0 to t. We have our partition. We have some function. And we approximate in this interval, we approximate the function by the left side value times the length of the interval. Yeah, we approximate it by the left side value times the length of the interval. And then one can show that, so we will do the hand waving here because, well, we can show it with the help of measure theory, etc. But here we will basically outline the approach. One can show that in the limit n to infinity, the integral from 0 to t of the distance between delta nt and delta t, the distance between the function and the simple process. So again, we approximate delta by simple processes. So the distance squared, the distance in absolute value squared, the integral, so in L2 that is, that this distance, when n goes to infinity, is equal to 0. Yeah? And this is what we call convergence in L2. So in fact, delta n converges in L2 to delta. Okay, now I can define the Ito integral. We used to have IT as the notation, but we often use that for simple processes. Now we can write the Ito integral as follows. The integral from 0 to t delta u dwu, we define it as the limit n to infinity of the integral from 0 to t of delta nu dwu, where delta nu are these simple processes, and our partition converges, which means we get an increasing number of points in our partition, and the mesh width in our partition gets smaller and smaller and converges to 0. Small t runs from 0 to t, and this is a convergence in L2. So it's the L2 limit of the sequence. So what you have to do is to approximate your function by simple processes. And for these, you know what the Ito integral is. And of course, it's an increasing sequence. And we will do a little hand waving here. Details are skipped, and I leave it to you to check the details if you're interested. But in fact, one shows then that delta n is Cauchy in L2. And based on that, we can prove the convergence, in fact. The most important thing here for us is that these are simple processes. And simple processes have really nice properties. So we will be looking at L2, at the L2 limit under the technical condition imposed. And that allows us to extend all the properties that we have for simple processes to these more general Ito integrals. And in fact, as mentioned, the Ito integral for these general adapted processes inherit the properties for the simple processes. And we will repeat these properties. Remember them because we will use them all the time. The first one was continuity. Yeah, for each omega. So we have an event. For each event, I t omega is a function of t, and it's continuous. Yeah, note that for simple functions, this follows from the continuity of the paths of the Brownian motion. Second one, adaptivity. So adaptiveness, right? The Ito integral IT, small t running from 0 to capital T, is adapted to the filtration script ft t greater equal to 0 of the underlying Brownian motion. Or in other words, IT is ft measurable. Third is linearity. Linearity is also interesting. So if we have IT defined as the integral from 0 to t of some function delta u dwu, and jt is defined as the integral from 0 to t of a function gamma u dwu, then a linear combination alpha it plus beta jt, written out as the integral from 0 to t alpha delta u plus beta gamma u dwu. In fact, the linearity property tells us that we can take the integral inside, and we can say this is equal to alpha times the integral from 0 to t delta u dwu plus beta times the integral from 0 to t gamma u dwu. So here is the linearity property. And fourth, the martingale condition, when IT is defined as our Ito integral for the general adapted processes, the integral from 0 to t of delta u dwu, t greater equal to 0, when that is in fact a martingale with respect to ft t greater equal to 0. And we also have the Ito isometry. And the Ito isometry for the, so you see all the properties for the simple functions, they are also properties of the Ito integral for the general adapted processes. So the Ito isometry in this case tells us the same as before, the expected value of I square, written out as the expectation of the integral from 0 to t of delta u dwu square. That is in fact Ito isometry. That is in fact the expected value of the integral from 0 to t delta square u du. And remember all these properties, they are important and we often see them. So let's recall, and we have a sixth one, a quadratic variation, that is written as follows, the quadratic variation of IT, the square brackets, I in square brackets t, that is the integral from 0 to t delta square du. And the differential notation, in fact, is dit is equal to delta square dt. Again, follows from Ito isometry, and it extends from the simple processes to the general adapted process. So let's go through them again. Continuity, adaptivity, linearity, the martingale property, Ito isometry, and the quadratic variation. Very important properties that we will often encounter. They are fundamental when we're dealing with an Ito integral for a general adapted process. So let's look at an example. And we will look at an example. We will determine an Ito integral. And in this case, our delta is just W. So we will calculate here the integral from 0 to t, wt dwt. So this is in a way analogous to the integral from 0 to t x dx. And we know that the integral from 0 to t x dx is 1/2 t squared. And we will see that this is a little differently here. And the reason is that we will have this quadratic variation. Yeah, it will take us a lot of work to solve this in this case. Because if we take a general process, we have to do it as a limit. Yeah? In the next video, we will learn a rule called the Ito-Dublin formula, which is similar to the product rule. And with this, we will also determine this integral, and in a much easier way. However, now we do not yet have it, so we have to work hard to get our solution. It is a little bit like with a derivative. First, you learn the definition of a derivative with the limit, function plus h minus the function divided by h. And you have to work hard to find the derivative. And later then you will learn the rules, the rules for derivatives. And then it's much easier to get the derivative because of the rules. So we do not yet have the rules, so we have to work hard. So here you see that my adapted process is the Brownian motion itself. And again, in the classical case, we would get 1/2 t squared over 2. So t squared over 2. But now, due to the quadratic variation, we will get an extra term. Now, on each piece, I'm going to define a simple process. So we do it with the definition that we just learned. So we are going to approximate WT by simple processes. And in this case, we do it with a simple partition. We take an equipartition. So we have our interval from 0 to t. We take a very nice partition. Yeah, equipartition. So we have our partition calligraphed P. It is I times T over N. And I is running from 0 to N. When I is equal to N, we are at the left side. When I is equal to N, we are at the right side. And this is an equipartition. All sizes of the intervals are the same. And then we define our simple process delta N as follows. We take the left side value, we have W. So in fact, it is a sum. I runs from 0 to N minus 1 of W at the left side point. That is W with as argument I capital T over N times the indicator function in that interval from I capital T over N to I plus 1 capital T over N. This is the definition of our simple process. And you will see that we have to work hard. Anyways, one can show that the limit n to infinity of the expected value of the integral from 0 to t of these simple functions, the functions that I've just defined, minus wt in absolute value square, right? That is equal to 0. Yeah, you can use the Lebesgue dominated convergence to make sense out of it, but here I just use this as a claim. Yeah, I just use it as a claim, claiming that the integral from 0 to t, wt dwt will converge in L2 and limit n to infinity, the integral from 0 to t, delta n t dwt. Yeah, and so in order to show that, we will write it out, but in order to make clear what is going on, I will start with a little different expression. Okay, we need to calculate the limit of the right-hand side, and for this we look at this special function over here. It is just a little bit more convenient to look at this function here, 1/2 the sum, I runs from 0 to n minus 1, wi plus 1 minus wi squared. And now see this notation, this is a short notation, w with a subscript I. For that, I mean w at the point, at the time point it over n. And that is just a little bit easier to handle. So we write this, and let's first look at this term, 1/2 sum I runs from 0 to n minus 1, wi plus 1 minus wi squared. So we will write it out. So we write the square out. So this is in fact 1/2, the sum again from 0 to n minus 1 of the first one squared, wi plus 1 squared, the last one squared plus wi squared, minus 2 times the mixed term, minus 2 wi plus 1 times wi. Now we can take the sum inside, and we can bring the sum inside. So this is 1/2 times this sum plus of minus this sum plus 1/2 times this sum. That is the next step. So we take this out. So it's 1/2 the sum I runs from 0 to n minus 1, wi plus 1 squared, minus the sum I from 0 to n minus 1 of the mixed term, wi plus 1 wi, plus the last term, 1/2 the sum I runs from 0 to n minus 1, wi squared. Now, in fact, what we have is here, if we look carefully, is we have a sum from 0 to n minus 1. When I is 0, we have w1 squared. And when I is equal to n minus 1, we have wn squared. So here we are dealing with w1 up to wn squared. Here, if we look carefully, we know w0 is equal to 0, right? So in fact, we can avoid or remove that part. So we have a sum which runs, I runs from 1 to n minus 1 of this term, wi plus 1 times wi. And here, if we look, so we have the sum I runs from 0 to n minus 1 of this. And 0, it's w0 squared. And in n minus 1, it's wn minus 1 squared. W0 is, of course, 0. So again, this can also run from 1 to n minus 1. And now, if we want to combine this first and this last term, we see that the only thing that is missing there is this nth term. This nth term is not here. So we can run from 1 up to n minus 1, and we can add them together, 1/2 of this one and 1/2 of this one. And we need to look at this nth term separately. So in our next step, we have this nth term separately. We use w0 is equal to 0. So we have 1/2 wn squared, the one that remains from this term, minus the mixed term runs from 1 to n minus 1, wi plus 1 times wi. And we have these two added, and that is a sum, I runs from 1 to n minus 1, wi squared. Now, looking at this carefully, we can combine these two, right? We can take the wi out, we can combine these sums, take the wi out, and then what we have, in fact, is, well, the first term just stays there, and what remains is, what we have here is minus the sum, I runs from 1 to n minus 1. We take wi out of the brackets here, of these brackets, wi times wi plus 1 minus wi. And this, if we look at it, this is in fact the definition of our delta n in this case. This is the definition of our integral, yeah, with the simple processes here. Remember that wi is w at the point I times t over n. And you can imagine that we can at some point take n to infinity, take the mesh width to 0, and that here we see something appearing. So in fact, this is the definition of what we have just seen. It is the integral delta n t dwt, the integral from 0 to capital T, of course. That is, in fact, the thing that we wanted. Here is our w, our dw, and here is wi, the left side point of this function. So this is, in fact, the one that we had with our partition n. And this one remains 1/2 wn squared. Now, so if we look at the start and the final part, in fact, we have reached something that we wanted to approximate. And we have reached our approximation of the Ito integral, our approximation with our simple functions and our partition. We have reached that. We could have done it in the reverse way. We could maybe have started with this and do all these steps like this, but this is quite a convenient formulation. But now we have a description for the integral that we wish to approximate. So we have a description. If we take this to the left-hand side, this to the right-hand side, then we find the description for our approximation of the integral. The integral from 0 to t of delta nt dwt, that is in fact 1/2 wn squared minus 1/2 the sum I runs from 0 to n minus 1, wi plus 1 minus wi squared. And we know this, right? These sums of Wiener increment square, they will go with dt. So how is the convergence going? Well, the convergence will then be by taking the limit as n to infinity and then convergence in L2. So here we repeat the thing that we just found on the previous slide, the integral from 0 to t delta n t dwt, that we have found that that is equal to 1/2 wtn squared, so wtn squared minus 1/2 the sum I runs from 0 to n minus 1, wi plus 1 minus wi squared. Now in limit, we will have this, right? So we have the function we desire in limit n to infinity, that will be equal to 1/2 w squared t minus 1/2 t. And this is in fact the term that we expect, 1/2 times the integrand squared. And this is an extra term, right? And then the convergence in L2 tells us that this approximation, this will converge in L2 to the desired Ito integral from 0 to t wt dwt. So what we have here is the classical part, the part that we expected, 1/2 times the integrand squared. And what we have here is the extra term due to the quadratic variation. And we have a classical part of the answer plus a part which is due to the quadratic variation. So indeed, the Ito integral is really different and it gives a different outcome than a Riemann integral or Lebesgue integral in this case. Now with the Ito Dublin formula, we will get this answer in a much faster way. That is then a rule to do the integration, and we will see that in the next video. Thanks for your attention.